Hi, this is the first part of, the second part of the video about derivatives and all that, increase decrease test, first derivative test, local minimums and maximums, inflection point, and concavity. So in my previous video, I forgot to finish and talk about the second derivative. There was also a question about the graphing. Of course, you can graph the function very quickly with plot. And as I was doing that, I realized that we probably did this in class, but that's okay. And then second derivative, sometimes, first of all, you need to compute second derivative. You can take a derivative of the first derivative, or you can just directly do diff f x and 2 for the second derivative. And sometimes solving inequality directly, as I did over here, works. So you can do that, and in the next example, I'm going to show you what you can do otherwise. A couple of tricks to help it solve the inequality or solve equality and interpret it yourself. In any case, this is second derivative. Second derivative is positive when x is less than 1, so it is concave up for x less than 1 and concave down elsewhere for x greater than 1. I should say for x greater than 1, because there is no point about there's no point to talk about concavity at x equals to 1. That is the inflection point where concavity is 0. And that is all I believe about that problem. That was a nice little problem. And now I'll move on to another problem that I just made. F of x equals to e to the power minus x times x squared minus x minus 1. Right away I plotted it, not much I can see from the plot, and I wouldn't be able to see some fun features of this function if I just look at one plot, or even know that there are some nice features here. How about I change my window and rerun this? Aha! So you see it has been negative and positive. So how about we try this? Interesting. So we have two intercepts, and actually we have our function becoming negative for a spell. We definitely see that somewhere around this point we will have an inflection point going from concave up to concave down. And there may be another inflection point. Since I know the behavior of this function, I think there should be another inflection point out there. So graphing and just looking at the graph is not always a good way to figure out everything about the function. So let's look here. Maybe now we will be able to see the other inflection point. How about I do 10? Here we go. So eventually it flexes. So there was one inflection point over there, and another should be somewhere around 6. Okay, so let us do this. Just a moment. Okay, so we have a graph here, and well, we start talking about the first derivative. And just to show you what's going on, if I just do show df1 is not going to be very pretty. Obviously, you can see here that e to the power minus x can be factored out, and the polynomial part can be simplified. If I just try to solve df1 equals to 0, I don't need to say equal to 0, it will work as is. It might not solve it. Oh well, it did solve. And well, it also solves the inequality right away. But to make it a little prettier, I can call factor on df1 and then look at the result. So the result will be much prettier if I factor first, since I saw from just looking at the expression that it can be factored. I'm going to factor it Um, Now, very nice. So it has been factored into this. All right, so from here it's also obvious where the zeros are, x equals 0 and x equals 3. And alternatively, we can figure out right away where the function is positive, where the function is negative. Where derivative is positive, where derivative is negative. And derivative is positive from 0 to 3, and hence the function is increasing on 0, 3, and decreasing on other intervals, that is decreasing from minus infinity to 0, increasing from 0 to 3, decreasing on 3 to infinity. So at x equals 0, there is a relative mean. At x equals 3, there is a relative max. We can actually add another cell and try the y values there. F of 0. Remember, we're plugging into the function itself here, not into the derivative, because ultimately we care about the function. Let me move this up. And that's what we want to understand. So 5e to the power minus 3. So yeah, this top of the hill is not very high, approximately 0.25. That is the approximate value for 5 times e to the power minus 3, apparently. All right. So we can also quickly see that this is not relative maximum. X equals 3 does not deliver a relative max because the function, when x goes to minus infinity, goes to infinity. So no absolute max. And as you can guess from this little curve over here, you know what will happen when x goes to infinity. Let me try to do that real quick. The function will go to 0. All right, so that means no absolute mean, because we had for a relative minimum. Oh no, actually wait. Let's wait here. Let's stop here and be a little bit more careful. F of 0 was delivering our relative minimum. The value was minus 1, and the limit of the function at infinity is 0. Hence, we do have an absolute and we do have an absolute mean at x equals 0. And the f of 0, as we saw earlier, is minus 1. So yes, if we look at values from, say, minus 1 to 10, we will see all those features probably relatively well. Yes, this is our absolute minimum. Okay. So going on to inflection points. Inflection points are, and concavity is about second derivative. I can take derivative of the first derivative, or call diff with 2 in the end. That would deliver second derivative as well. And as well, it is not very readable as is. We would want to factor it. So here we go. We factored it, and we have a quadratic times e to the power minus x. If I try to solve bigger than 0, it might not work, and you see that the x values, the exact x values, are not whole numbers, so that might actually thwart it. So we will have to solve the equality and then figure out the values on each side of the interval. So this is presumed inflection points. Candidates for inflection points, that is when second derivative is 0. And now we need to figure out concavity. So this is half of square root of 13 plus 5 over 2. The easiest way to do it is maybe to see what's happening at minus infinity. So limit of second derivative. Instead of actually plugging in a value, maybe I should plug in a value. Okay, change of plan. df2 of minus 100. Let me see what that is. That is positive. So to the left of this value, my function is concave up. And all right, it took me a moment to realize what's in between these two values. Obviously, the first one is smaller because of the negative over here, and the second is larger. I don't necessarily know if 0 is in between. It may well be the case. Actually, no, 0 is not in between, but I certainly know what is in between. So maybe pause the video and think of a nice value in between these two to plug in. I'm giving you this time to do that. And the value is 5 over 2. That is because we have 5 over 2 minus something for one x value and 5 over 2 plus same thing in the other value. So 5 over 2 is certainly in between. We can compute the second derivative negative. And very similarly, on the last interval, which is going to plus infinity, let's just plug in 100, get a huge positive value. And here we go. We can write a conclusion. Concave up on minus infinity to this value. I'll just copy paste it. Comma, the other interval starting from the same thing with plus to infinity. And concave down on the interval in between. So I'm just copy pasting from here and I'm making it into the interval. Just delete that, and here is my interval. Consequently, these two x values are actually found to be what? Inflection points. Inflection points. All right, and that actually coincides with our prior discussion of how this function bends, and we talked that there is one inflection point over here and one inflection point somewhere over here. And that's it for this sort of videos, and I should be able to publish this code in notebooks for you to look at.